Earlier we looked at the box plot and we see it's a very intuitive and visual way to display 5 number summary of a variable. And in this section, we're going to look at a few more graphic displays that can depict the basic statistical description data for 1 or 2 variables. So box plot we already talked about. Next, we're going to look at a quantile plot and a quantile plot, also called QQ plot. We're going to look at a bar chart and a histogram. Those two are very similar, and you often see they being confused in the literature, on the web, and even in our textbook. So I think I will spend some time to compare and contrast those two. The scatter plot is all the other plot types that we introduced earlier are focused on univariate distribution. For scatter plot, we actually could treat bivariate data or data with 2 variables, observations that's been described using 2 attributes or 3 attributes. We could use those. Scatter plot is a powerful tool for us to review correlations among the variables in our data set. So let's move on to talk about the quantile plot. Quantile plot conveys the information that's very similar to a box plot, 5 number summaries. However, it gives you a little bit more detail than the box plot because it allows you to display all of the data points. So here we have one variable, unit price. This could be unit price of all the items sold in certain store. A quantile plot can show the minimum value, the largest value, and all the percentiles. The way that we plot a quantile plot is to first sort the data in order from small to large. And then for every data value, we compute what percentage of the data point is smaller than or equal to this current value. And we plot that percentage on the x-axis. That's the f value or the frequency. So we can compute f by simply using the order of the current value divided by the number of total data points that we have. This probably will not give you the prettiest quantile plot, so there are minor modifications of this simple formula. You can plus 1 in the to the n or minus a small number to the I, or I also see I plus 1 and n plus 1, I minus 1, n minus 1. So all sorts of variation give you very similar plot. So what this illustration, this plot tells us that we can find the like 25% of the data is below, 25% of the items were sold under $60 per unit, right? So this is our Q1. And we can find the median price, unit price of all the products that we have. So if we go up here and we can find maybe our average median unit price is at $80 per item. and you can find your Q3 here. This is the maximum value, so mean, max. It gives you the summary, and also you can see if there is major gaps. The gaps will only occur on the vertical, on the y-axis will never occur on the x-axis because we for every data point we compute um, um, the percentile, and this I is always increased by 1, right? When we compute the next the fi for the next item. Okay. Quantile plot is not frequently used alone by itself because it does not really offer a lot of information beyond the box plot. But it is really a very fun, it's a foundation to create a more powerful plot. For example, the QQ plot. Quantile plot allows you to compare two univariate distribution. So in this case, we have two variables. We have, well, we should see we have two univariate distribution. So one is the unit price from branch 1 of our store. Let's see, our store have n branches. From branch 1, the product has the unit price from $40 to $120, and branch 2 sells the same set of items, and they use different set of prices. So we can see whether those two univariate distribution are similar or are the same. So the way that we plot this is we first again sort the values. Unit price are sorted in all the unit prices in branch 1 are sorted in an increasing order, and we do the same for branch 2. Then we pair up those individual values. So the smallest value is paired up. Smallest price from unit branch 1 is paired up with the smallest unit price from branch 2. And the second smallest unit price is paired up with the second smallest unit price in branch 2. And we do the same for the rest of the unit prices. This will generally give you a two-dimensional plot whereby examine the shape that's created by those dots data points in the graph. You can tell whether those two univariate distribution are the same. If they form a straight line, then their distribution are the same. In this case, we see that at the lower end, the upper end, they falls onto the line, but in the middle part, there is a visible curve. So we can see that for many items, the unit price items sold at branch 1 tend to be lower than those at branch 2. This is one usage of the quantile plot. Another more typical and well-known usage of quantile plot is to plot one univariate distribution against a known distribution. So we might have the price from branch 2, and we could actually generate a set of data points, a set of values from a normal distribution. Then we can sort those two data sets and pair the values up and plot a similar plot, which will be able to tell us whether branch 2 unit price follows a normal distribution. Because if the plot creates a straight line, we know that the distribution of the unit price from branch 2 is the same as the distribution that's given, which is normal. So that's probably the second and probably more often used uh, application of Quantile Plot. Okay. You could have one variable has more values than the others. When you, in that cases, you will sort the two data set and yet just to plot, just take the smaller number of the two as the number of the dots that you're going to plot on this graph. Okay, so we talked about quantile plot. The next thing we want to talk about is the bar chart and the histogram. I think it's always better when we have a clear definition for certain things, we stick to it. I hate to blur those definitions and make things very, very confusing. Histogram has a very clear definition. Bar chart too. And those might look like the same, but they represent quite different concepts. So I think we should make an effort to distinguish those. So histogram is used to show the probability distribution of a given variable. Like histogram is approximation of the normal curve that we drew earlier. We're going to draw our frequency of certain data value occurs as a curve that can show the distribution of the data. On the other hand, the bar chart is used more widely than histogram. Bar chart can depict the frequency or counts, but they really carry quite different meanings. So I listed here some of the differences, the key differences. But we can first probably look at one example of histogram and an example of bar chart. So this histogram depicts the dollar amount per transaction in a business. So some transactions are more, how am I going to say that? So more items being bought in one transaction, so the dollar amount involved is greater than others. And if we plot this as a histogram, the x-axis has the dollar amount ranges. The y-axis depicts the density. Okay, so here what we can see is 60% of all transactions involves less than $1,000. So here it's between $0 and $1,000, and 20% of transaction involves a dollar amount that's between $1,000 to $2,000. So this gives us a distribution. We can see that majority of the transaction are within $1,000. Okay. What we can see here, our dollar amount is a continuous variable, that there is not a gap in between those bars because the value are continuous. And the vertical axis, the y-axis, can be frequency, density, or count in this case. How many transactions, for example, involve certain dollar amounts. On the other hand, when we look at this bar chart, what we notice is, well, bar chart can use count or percentage too. but it can be any other values or variables on the y-axis. So in this case, this is average, I don't know, price, average, this looks like price. And the x-axis are not continuous variables. In this case, we have nominal variable. So the values are check, credit cards, debit cards, digital wallet, and cash. You can show those because those are nominal variables. They make no sense to connect them. There has to be a gap because they're unique, distinct values. And also, when we have unique, distinct values, the order of this would not matter. You can put cash in front of check or after credit card. That's your preferences. You can sort based on this, but that does not meaning cash is anything, you know, better or worse than any other way of payment. The other thing that we want to notice is the width. For bar chart, because the bar really just represents certain things, the width of the bars are typically the same in a bar chart. However, in a histogram, the width could be different depending on your design. In this class, we're going to talk about equal width and equal depth histogram. When you have equal depth histogram, the width can be different. So to summarize what we have talked about, histogram plots continuous variables. Bar chart plots are for discrete variables. Histograms does not have gaps between bars. All the bars are adjacent to each other. Bar chart has separated bars, there are gaps between the bars. Bar width are consistent in a bar chart. They have equal width bars. In histogram, they don't have to. Histogram can have very width. And the orders of the bars in histogram, it certainly matter because the value is always from the smallest to the greatest, right? However, in a bar chart, the bar order really does not. It can be arranged to convey certain information, but thematically, the order does not matter. There is not a coherent, defined order in those bar charts. So, okay. Another point on histogram that I want to make is that histogram offers more than box plots. The example given here, we can see these two variables have different distribution. We can see from their histogram. One is more of a normal looking. The other has bimodal. So the distribution are different. However, if you look at their 5 numbers summary, you will see they have the same minimum value, same maximum value, same Q1, same Q3, and the medium is most likely to be the same as well. The box plot, the box plot or the 5 number summary will give you exactly this, will tell you those two distributions are identical, but they're not. If you plot the histogram, you're going to see the difference. So therefore, it's safer to plot histogram than just looking at box plots. Okay. So the last plot that we're going to introduce is the scatter plot. This scatter plot is a powerful tool. What the example that I use here is example for bivariate numerical data. So meaning that the observations is described by two variables. So in this case, we have some products. Each product has a unit price, and each product also have a number of items sold. So we can plot these two variables in one plot, and this plot will give us more information than any other plots that we have seen so far. So what we can see here, so this is our first product. It has this unit price, and it has been sold 300 items. And this has about close to $8 price, and we sold it close to 400 items, maybe in a week. What does this plot tell us? We can see from this plot potential relations between unit price and items sold. We can see that the price, the products that's the cheapest or the most expensive, they are sold at smaller amount. While the price in the middle range, those products with price in the middle range sold more than the most expensive or the least expensive ones. Okay, we can see that when price increase to some extent, our sale actually increase. But when we reach certain price, which is like $80, then the amount of sale drops. Okay, so this gave us more information than what we could gather from the previous plot, because it shows two variables in one plot. It depicts the relationship quite visually. Because we can also plot in 3-dimensionals, as you can see. If you have a trivariate numerical data set, then you can actually compare, look at the relationships among 3 variables just by plotting the data into a 3-dimensional space. So here we look at one sort of a correlation between two variables, items sold and unit price. I want to show you visually a number of other examples. This is the one that we just saw, but in this case, this plot shows, I did not draw, tell you what variables are on x-axis and y-axis. That doesn't matter. Because what we really want to show with these plots is that we know by looking at this plot, there is a strong linear correlation between those two variables, no matter what they are. We see a clear positive linear correlation. The greater the value on x-axis, the greater the value on y-axis. This example depicts a negative linear correlation fairly strongly, where we can tell that the greater the values on x-axis, the greater the value on x-axis, the smaller the value on the y-axis. So those two variables are negatively correlated. Okay. So those two represents linear correlation because we can draw a straight line. The data shows a straight line. And this data is also correlated, but our line, we can't really draw a line to fit all the data, but we can draw a curve. So it's correlated, but not linearly correlated. Okay. If the data is actually not correlated, you're going to see something like this. The data seems to be randomly distributed within the data range that we have, that we can't really, fitting a line does not make any sense here, because a line can be fitted anywhere, and we see lots of things not falling onto that line. So those 3 examples show uncorrelated data when you actually plot them in a uncorrelated variables, the x and y axis are not linearly or in other way correlated. Okay, this concludes this little video.